There are ideas scientists rarely describe as impossible. They use more careful words: unresolved, speculative, incomplete. Behind that language lies a collection of theories capable of changing our understanding of time, matter, consciousness, and reality itself. Far beyond the blue atmosphere of Earth, where sunlight gives way to an almost perfect blackness, galaxies drift through an expanding universe. Their light travels for millions and billions of years before reaching our telescopes, carrying with it a record of cosmic history. Yet, the farther scientists look, the more unsettling the behavior of the universe becomes. Space itself is expanding. That fact is no longer a matter of speculation. In the late 1920s, observations associated with Edwin Hubble helped establish that distant galaxies generally appear to be moving away from us, with more distant galaxies receding faster. The universe was not static. Its enormous structure was changing on the grandest scale imaginable. For decades, however, astronomers believed that gravity should gradually slow this expansion. Every galaxy, every cluster, every concentration of matter exerted gravitational influence. Given enough time, it seemed reasonable that this attraction would place the brakes on the cosmic expansion. Then came one of the most important discoveries in modern cosmology. In the late 1990s, observations of distant Type 1a supernovae indicated that the expansion of the universe is accelerating rather than slowing down. Independent observations later strengthened that picture. Something appeared to be driving space apart on increasingly large scales. Scientists gave this mysterious component a simple name: dark energy. The name sounds definitive, but it is not. Dark energy is not a substance that has been directly collected, photographed, or examined in a laboratory. It is a term describing whatever is responsible for the observed accelerated expansion within our current cosmological models. Its fundamental nature remains unknown, and this is where the Big Rip enters the story. The idea was developed in the early 2000s by cosmologist Robert Caldwell and his collaborators. Their model explored an extreme possibility involving dark energy. What would happen if its density increased as the universe expanded? Under the standard cosmological picture, dark energy behaves approximately like a cosmological constant. As space expands, its density remains roughly constant. But there is another possibility. Dark energy could possess an equation of state parameter, usually represented by the letter W, with a value below -1. This regime is often described as phantom energy. The distinction may seem mathematical, but its consequences are enormous. If such a form of dark energy exists and remains dominant, the expansion of the universe would not simply continue. It would become progressively more powerful. As the universe grew larger, the repulsive effect associated with this form of dark energy would intensify. At first, almost nothing would appear different. Galaxies separated by enormous distances would continue drifting apart. The cosmic web would slowly become more isolated. Regions of space that are already moving beyond our observable horizon would disappear from view. Then the process would become more extreme. Galactic clusters could eventually be pulled apart. Individual galaxies could lose their gravitational cohesion. Stars could become separated from their stellar systems. Eventually, the increasing expansion could overwhelm the gravitational forces holding planets around stars. But the Big Rip does not stop there. If the model were correct, even the forces binding matter together could eventually be overcome. Atoms themselves could be disrupted. The distinction between this scenario and an ordinary expanding universe is therefore profound. Expansion would not merely rearrange the contents of the cosmos. It would progressively overcome the forces that maintain structures at every scale. The universe would be dismantled from the largest structures downward. There is something almost counterintuitive about this prediction. We normally associate destruction with collisions, explosions, gravity, or the collapse of massive objects. The Big Rip proposes something entirely different. Nothing would need to strike the Earth. No star would need to explode nearby. No black hole would need to consume the solar system. The fabric of cosmic expansion itself would become the destructive mechanism. But before such an image is taken too literally, an important distinction must be made. The Big Rip is not an established prediction of modern cosmology. It is a theoretical possibility that emerges from a particular model of dark energy. Current observations do not establish that dark energy is phantom energy, nor that its density must increase indefinitely. In fact, the simplest and most widely used cosmological model treats dark energy as approximately constant over time. So, why does the Big Rip continue to attract scientific attention? Because the nature of dark energy remains one of the great unresolved problems in cosmology. Scientists can measure its apparent influence on the expansion of the universe without yet knowing precisely what dark energy actually is. That creates an unusual situation. We have strong evidence for accelerated expansion, but the underlying mechanism remains uncertain. The mystery lies not in whether the universe is expanding faster than expected. It lies in why, and that question leaves room for several possibilities. Perhaps dark energy is simply a cosmological constant, a property of empty space that remains stable across cosmic time. If so, the universe would continue expanding indefinitely, becoming colder and more dilute over immense stretches of time, but it would not experience a Big Rip. Perhaps dark energy evolves. If its behavior changes as the universe ages, the ultimate fate of the cosmos could be very different from what the simplest model predicts. And perhaps our present understanding of gravity itself is incomplete. Some cosmologists have explored modifications to general relativity that could produce effects resembling dark energy without requiring a conventional dark energy component in the way the standard model describes it. The Big Rip therefore occupies an interesting position in science. It is neither established fact nor pure fantasy. It is a mathematical consequence of a particular set of assumptions about the universe. That distinction matters. Science often advances by examining precisely these possibilities. A theory can be improbable and still useful. It can reveal what observations would need to show in order for a particular scenario to become plausible. By calculating the consequences of an extreme model, researchers can compare those predictions against measurements of the real universe. The Big Rip provides an especially dramatic example. Imagine the universe billions of years from now. The Milky Way, assuming its future interactions proceed as expected, would no longer resemble the galaxy we see today. Distant galaxies would gradually become inaccessible as accelerating expansion carried them beyond the observable horizon. The night sky would lose many of its familiar companions. Eventually, under the Big Rip scenario, the gravitational bonds within cosmic structures would no longer be strong enough to resist the accelerating expansion. Galaxies would separate. Then stellar systems. Then planets from their stars. As the expansion rate continued increasing, smaller and smaller structures would become vulnerable. Near the hypothetical final stage, even atomic structures could cease to remain intact. The exact sequence depends on the parameters of the model, particularly how far below -1 the equation of state parameter lies. The more extreme the phantom energy behavior, the sooner the hypothetical final event would occur. Some versions of the model place the final disintegration tens of billions of years in the future. But this is not a prediction that scientists currently expect to happen. It is a consequence of assuming a particular form of dark energy continues unchanged. And that assumption is precisely where the uncertainty lies. What if dark energy changes? What if the apparent acceleration we measure today represents only one phase in a much longer cosmic evolution? What if the universe eventually approaches a state in which expansion behaves differently? There is another reason the Big Rip is fascinating. It forces us to confront the difference between what we can observe and what we infer. Astronomers do not watch galaxies being pushed apart by an invisible force in the conventional sense. Instead, they measure distances, redshifts, cosmic expansion, supernova brightness, the cosmic microwave background, and the distribution of matter across enormous scales. From those observations, mathematical models are constructed. Those models describe a universe whose large-scale behavior can be predicted with remarkable precision. Yet, beneath that success is an unanswered question. What is driving the acceleration? Dark energy accounts for roughly 70% of the present cosmic energy budget in the standard cosmological model, while ordinary matter makes up only a small fraction. The rest is generally attributed to dark matter, another component whose nature remains unknown. In other words, the overwhelming majority of the universe is associated with things we do not yet fully understand. That does not mean cosmology is failing. It means the frontier is larger than the territory already mapped. The Big Rip takes that uncertainty to its most extreme logical endpoint. It asks us to consider what the universe might become if one particular interpretation of dark energy were correct and remained stable over unimaginable spans of time. There would be no final battlefield, no single catastrophic explosion, no central point where everything collapses. Instead, the universe would gradually lose its ability to hold itself together. First, on the scale of galaxies, then stars, then planets, finally matter itself. And yet, there is an important possibility that makes the story even more intriguing. The Big Rip may never happen at all. Future observations could show that dark energy behaves almost exactly like a cosmological constant. They could reveal that its properties evolve over time. They could expose weaknesses in our current theories of gravity. Or they could uncover something entirely different, forcing cosmologists to rewrite the story once again. For now, the universe continues its expansion. Galaxies remain scattered across unimaginable distances. Stars continue burning inside them. Planets continue orbiting their suns. And here, on a small world around an ordinary star, scientists are attempting to determine what that expansion ultimately means. The equations can describe several possible futures. Observation will decide which one belongs to reality. Until then, the Big Rip remains suspended between mathematics and the unknown, a scenario built from real observations, but dependent on a form of dark energy whose true nature has yet to be revealed. And somewhere in the immense darkness between the galaxies, the universe continues to expand, carrying with it a question that remains open. How much of its ultimate fate is already written into the laws we have discovered, and how much is still hidden beyond our understanding? Far beyond the last familiar lights of Earth, the universe unfolds as an immense field of galaxies, each separated by distances so vast that ordinary human intuition begins to lose meaning. The darkness between them is not empty in the simple sense. It contains radiation, invisible matter, magnetic fields, and perhaps the influence of whatever drives cosmic expansion. For more than a century, astronomers have been learning that this enormous structure is not fixed. Space itself changes. Galaxies generally recede from one another as the universe expands, a discovery established through observations in the early 20th century. Edwin Hubble and other astronomers helped reveal that distant galaxies exhibit systematic redshifts, providing evidence that the cosmos was expanding on the largest scales. But expansion was never the only possibility. For much of modern cosmology, another fate remained mathematically conceivable. Perhaps the universe would eventually reach a turning point. Perhaps expansion could stop. And perhaps, after stretching outward for billions of years, the entire cosmos could begin to fall inward. This is the Big Crunch. The idea belongs to an earlier generation of cosmological thinking, when the ultimate destiny of the universe was closely tied to one deceptively simple question: is gravity strong enough to reverse cosmic expansion? The logic was straightforward. The universe contains matter. Matter possesses gravity. Gravity attracts. If enough matter existed, its collective gravitational influence might eventually overcome the outward expansion initiated by the early universe. The cosmos would slow. The expansion rate would approach zero. Then the direction of cosmic evolution would reverse. Galaxies that had spent billions of years separating would begin moving toward one another. Large-scale structures would become increasingly compressed. Temperatures would rise as matter and radiation were forced into a progressively smaller volume. The universe, once enormous, would begin folding back toward an increasingly dense state. But this elegant picture depends on something crucial: the overall dynamics of cosmic expansion. For decades, cosmologists investigated whether the universe contained enough matter to make eventual recollapse possible. The concept of a critical density became central to these discussions. Depending on the geometry and energy content of the universe, different long-term outcomes could emerge. A universe with sufficient gravitational influence might eventually reverse its expansion. Another might expand forever. The distinction seemed to depend heavily on the amount of matter and energy distributed across cosmic space. Then, observations changed the conversation. In the late 1990s, studies of distant Type 1a supernovae produced an unexpected result. Rather than gradually slowing under the influence of gravity, cosmic expansion appeared to be accelerating. The discovery transformed the problem. Something resembling a repulsive component seemed to dominate the large-scale evolution of the universe. That component became known as dark energy. Under the standard cosmological model, dark energy behaves approximately like a cosmological constant. If that description remains accurate indefinitely, a traditional Big Crunch becomes difficult to achieve. Continued accelerated expansion would prevent the universe from reversing course. Yet the story is not quite closed, because dark energy remains one of the deepest unresolved questions in cosmology. Scientists know its apparent effect. They do not yet know its fundamental nature. That distinction leaves the ultimate fate of the universe less certain than the equations might initially suggest. Suppose dark energy were not constant. Suppose its influence changed over cosmic time. Suppose the physics governing the expansion of space evolved in ways our current models do not capture. Under certain theoretical scenarios, cosmic acceleration could weaken or disappear. In more speculative possibilities, the large-scale dynamics could eventually favor contraction. The universe would then possess a cosmic turning point. There would be no dramatic boundary separating expansion from collapse. Instead, the transition could unfold across immense stretches of time, almost imperceptibly at first. The expansion rate would decline. Galaxies would stop gaining distance from one another at the same accelerating pace. Eventually, the outward motion would reach a maximum. For an observer living through that era, the universe might not announce its transformation with any obvious signal. The sky would simply begin telling a different story. Over immense periods, distant structures could draw closer. The cosmic background radiation would become increasingly compressed and energetic. As contraction intensified, matter would occupy progressively smaller regions of space. Temperatures would climb. Galaxies would collide with greater frequency. Stars could encounter increasingly hostile environments as gravitational interactions rearranged stellar systems. Black holes could merge. The architecture of the cosmic web would gradually disappear beneath increasingly extreme density. Eventually, the universe would become radically different from the cold, diffuse cosmos visible today. And here, the Big Crunch begins to resemble the opening chapter of the universe itself. The early cosmos was extraordinarily hot and dense. As expansion proceeded, temperatures fell, particles combined into increasingly complex structures, and eventually stars and galaxies emerged. A Big Crunch would reverse that broad progression. Matter would be compressed. Radiation would intensify. Structures that required enormous cosmic distances to exist would lose their stability. The distinction between separate galaxies would become meaningless. The universe would become hotter, denser, and increasingly dominated by extreme physical conditions. But would the contraction continue all the way to a final, singular state? That is where certainty begins to dissolve. General relativity permits solutions involving extreme gravitational collapse, but our current theories are incomplete under the most intense conditions. General relativity describes gravity remarkably well on many scales, while quantum mechanics governs the behavior of matter and energy at microscopic levels. A complete theory combining both has not yet been established. So, the deepest stage of a hypothetical Big Crunch lies beyond a region where existing physics can provide a confident description. Perhaps the universe would collapse toward a state of extraordinary density. Perhaps quantum effects would become dominant and prevent a true singularity. Perhaps contraction could trigger another expansion. This last possibility leads to an even more intriguing idea: the Big Bounce. In some cosmological models, a contracting universe does not end in an absolute beginning or final point. Instead, the collapse reaches an extreme state, and some mechanism causes the cosmos to rebound into a new phase of expansion. If such a scenario were possible, the universe could possess a cyclic character: expansion, contraction, compression, re-expansion, then another cosmic era, and another. The concept has appeared in various forms throughout the history of cosmological thought, although modern versions rely on very different physical mechanisms than older philosophical notions of an eternal cosmic cycle. Some models arise from attempts to modify or extend general relativity. Others emerge from quantum cosmology or theories involving conditions at extremely high density. None has been established as the description of our universe. That distinction is essential. The Big Crunch is not a prediction supported by current evidence in the same way that cosmic expansion is. The observed acceleration of expansion presents a major obstacle to the simplest form of the scenario. Yet, scientific history has repeatedly demonstrated that apparently settled assumptions can be revised when new observations arrive. The accelerating universe itself was once an unexpected discovery. Before the supernova observations of the late 1990s, many cosmologists expected the expansion to be slowing. Nature offered a different result. That history provides an important lesson when considering cosmic destiny. Our models describe the universe as far as our measurements allow. They do not guarantee that the final chapter will resemble the one currently favored. There is another subtle feature of the Big Crunch worth considering. The universe does not require a dramatic external force to collapse. No invisible hand would need to pull the galaxies inward. The behavior would emerge from the fundamental dynamics of space-time, matter, and whatever form of energy governs cosmic expansion. In that sense, the Big Crunch is less an invasion of destruction than a reversal of cosmic behavior. The same universe that once expanded would begin contracting under a different balance of forces. The enormous distances between galaxies would cease to increase. Then they would shrink. The vast emptiness that defines the present cosmos would gradually become less empty. Yet, whether such a reversal is physically possible remains uncertain. Measurements of the cosmic microwave background, galaxy distributions, gravitational lensing, supernovae, and other observations continue to refine our understanding of cosmic expansion. Researchers are also investigating whether dark energy truly behaves exactly like a cosmological constant, or whether subtle changes might eventually appear. Those measurements matter because the fate of everything may depend upon a property of the universe we still cannot directly identify. If dark energy remains constant, the Big Crunch may remain only a mathematical possibility. If its behavior changes, the cosmic future could become more complicated. And if the laws governing gravity themselves require revision at the largest scales, even our present categories of cosmic endings may prove inadequate. Perhaps there is another possibility that has not yet entered the equations. Perhaps the universe does not fit neatly into the alternatives we have imagined: endless expansion, catastrophic contraction, or cyclic rebirth. The history of cosmology offers reasons for humility. Every generation observes the cosmos through the instruments available to it, builds models from those observations, and eventually encounters evidence that exposes the limits of what came before. The universe has already surprised us. Its expansion was unexpected, its acceleration was unexpected, its dark components remain unexplained. And the deeper scientists look into the question of cosmic destiny, the more it becomes clear that the final outcome depends upon physics operating on scales and times far beyond ordinary human experience. For now, the galaxies continue their outward journey. The universe remains vast, cold, and expanding. But written into the equations is another possibility, a cosmos that could one day reverse its direction, gathering its scattered structures into an increasingly compressed whole. Whether that fate belongs to reality or merely to the mathematical landscape of possibilities remains unresolved. Perhaps the most intriguing part is that the answer may already be encoded in the behavior of dark energy, waiting for future observations to reveal what it truly is. Until then, somewhere beyond the reach of our telescopes, the universe continues writing a story whose final page remains hidden. At the edge of everything we can see, galaxies hang like distant islands in a darkness too immense for ordinary language. Their light has crossed billions of years to reach us, carrying evidence of a universe that was once far hotter, denser, and younger. Every observation seems to point backward toward an extraordinary beginning. But perhaps that beginning was not the beginning. Perhaps the universe we inhabit emerged from something that came before it. The idea sounds almost impossible at first, yet it arises from a serious problem in modern cosmology. If the universe began in an extremely hot and dense state, what happened at the earliest moment? What existed before that state? And does the word "before" even make sense when time itself may have emerged with the cosmos? The standard Big Bang model describes the evolution of the universe from an early hot, dense condition. It has been remarkably successful. Observations of the cosmic microwave background, the abundance of light elements, and the large-scale distribution of galaxies all provide strong evidence that the young universe was radically different from the one we see today. But the Big Bang model is not necessarily a complete description of the absolute beginning. Run the equations of general relativity backward, and cosmic expansion eventually leads toward an extreme condition of density and temperature commonly associated with a singularity. At that point, the mathematical framework we normally use to describe gravity ceases to provide a reliable physical picture. The equations have reached a boundary. Physics has not yet crossed it. That unresolved boundary is where the big bounce becomes particularly intriguing. Rather than treating the early universe as the absolute beginning of existence, bounce cosmologies propose a different possibility. Perhaps a previous universe, or an earlier phase of our own cosmos, underwent contraction before reaching an extreme state and then transitioned into expansion. The universe may not have begun. It may have turned around. This distinction changes almost everything. Picture a cosmos expanding for billions of years. Galaxies separate, space grows, temperatures fall, structures emerge, stars ignite and eventually fade. On an unimaginable timescale, the universe could enter a phase of contraction. Distances would decrease. Matter would become increasingly compressed. Radiation would grow more energetic. The cosmic environment would become hotter and denser. Yet, instead of allowing the collapse to proceed toward an infinitely dense singularity, some unknown physical mechanism would intervene. At the most extreme moment, contraction would cease. Expansion would begin again. A bounce. The concept is not simply an attempt to give the universe a poetic origin story. It emerges from attempts to address one of the deepest conflicts in theoretical physics. Our best descriptions of gravity and quantum mechanics do not yet form a complete unified theory under the extreme conditions expected near the earliest moments of cosmic history. General relativity describes gravity as the geometry of space-time. It has passed extraordinary observational tests, from the motion of planets to gravitational waves produced by merging black holes. Quantum mechanics, meanwhile, governs matter and energy at microscopic scales with astonishing precision. But when gravity becomes extraordinarily strong and quantum effects cannot be ignored, the two frameworks become difficult to reconcile. The earliest universe may have been precisely such a place. That is why some physicists have explored theories in which quantum effects modify the behavior of gravity at extreme densities. One example comes from loop quantum cosmology, an approach inspired by loop quantum gravity. In certain mathematical treatments, spacetime itself has a discrete structure at incredibly small scales. Under those conditions, gravitational effects can behave differently from what classical general relativity predicts. Instead of collapsing endlessly toward a singularity, the universe could reach a maximum density and then rebound. The singularity disappears. The collapse becomes a transition. Other approaches have produced different versions of the same broad possibility. Some string-inspired cosmological models have considered pre-Big Bang phases. Certain ekpyrotic and cyclic models propose repeated cosmic episodes involving contraction and expansion, sometimes connecting these processes to higher dimensional physics. These ideas are diverse and should not be treated as interchangeable. They share a family resemblance, not a single mechanism, and none has been confirmed as the actual history of our universe. That uncertainty is important because the Big Bounce is often presented as though science has discovered evidence of a previous universe. It has not. There is currently no direct observation showing that our universe underwent an earlier contraction phase. What exists instead are theoretical models asking whether such a history can emerge naturally from plausible extensions of known physics. The distinction between evidence and possibility is one of the most important principles in cosmology. Still, the question remains compelling. If a bounce occurred, what came before it? Was there another universe? Was it the same universe in an earlier phase? Could physical laws have remained unchanged across the transition? Or might a previous cosmic cycle have left subtle traces in the universe we observe today? Those questions have led researchers to examine the possibility that an earlier phase might leave fingerprints in the cosmic microwave background. The microwave background is one of the oldest electromagnetic signals we can observe. It comes from a time roughly 380,000 years after the universe entered its hot Big Bang expansion phase, when conditions allowed light to travel freely through space. It provides an extraordinary snapshot of the early cosmos. If a pre-Big Bang phase somehow influenced the conditions that produced this radiation, perhaps faint statistical patterns could survive. But finding such a signature would be extremely difficult. The early universe underwent enormous changes. Inflation, reheating, structure formation, gravitational interactions, and other processes could alter or obscure any primordial information. A signal from an earlier cosmic phase, if one exists at all, might be extraordinarily faint, and even a suspicious pattern would require careful examination. Could it truly be evidence of a previous universe? Or could it emerge naturally from ordinary cosmic processes? Cosmology has repeatedly demonstrated how easily apparent anomalies can become complicated when viewed through better data. That is why researchers remain cautious. The Big Bounce also raises a profound question about time itself. If the universe underwent a contraction phase before expansion, then time may extend beyond the period commonly described as the beginning of the Big Bang. Our universe would possess a history before the history we usually call cosmic history. But perhaps the concept of before is itself inadequate. If the physical nature of time changes under extreme gravitational and quantum conditions, then asking what happened before the bounce may be comparable to asking what lies north of the North Pole. The language may fail before the physics does. There is another possibility. Maybe each bounce does not reproduce the universe exactly. Perhaps physical conditions change from one cycle to another. Entropy could accumulate. Quantum fluctuations could alter the distribution of matter. Different cosmic cycles might develop different structures. This introduces the problem of entropy. The second law of thermodynamics tells us that entropy tends to increase in an isolated system. A perfectly repeating universe would therefore face a difficult question. If cycles continue indefinitely, how can each one resemble the previous one without accumulating an ever-growing thermodynamic imbalance? Different cyclic models attempt to address this problem in different ways. Some propose mechanisms that dilute or reset certain features of the previous cycle. Others construct cosmological scenarios in which entropy behaves differently across enormous periods. None has provided a universally accepted answer. The difficulty is not merely philosophical. It reaches into the mathematical architecture of the models themselves. A cyclic universe must explain how a previous cosmic phase can transition into another while remaining compatible with the laws of thermodynamics, quantum mechanics, and gravity. That is an extraordinary demand. And yet, the appeal of the Big Bounce is partly rooted in its ability to replace one profound mystery with another. The standard picture asks why the universe began in its initial, hot, dense state. The bounce scenario asks what physical process produced the transition into expansion. Neither eliminates mystery. It relocates it. There is also a remarkable conceptual shift hidden inside the idea. The Big Bang is often imagined as an explosion occurring at a particular point in space. Modern cosmology describes something more subtle. Space itself expanded, and the early universe was extremely hot and dense throughout the observable region. A bounce would not be an explosion inside an existing cosmic arena. It would be a transformation of the universe itself. There would be no central location where the rebound occurred. Every region would participate in the cosmic transition. That makes the concept difficult to visualize. Imagine compressing not merely matter, but the geometry separating all matter. The distances that define galaxies, stars, and planets would become progressively smaller. The familiar architecture of space would lose its meaning as the universe approached its most extreme state. Then something would change. Expansion would return. The arrow of cosmic history would point outward again. From that transition would emerge the universe we now observe. Whether that is physically possible remains unknown. Observations continue to constrain cosmological models. Measurements of the cosmic microwave background, galaxy clustering, gravitational waves, and the expansion history of the universe provide increasingly detailed information about the cosmos. So far, none has established that a previous cosmic cycle existed. But the absence of evidence is not a proof that such a phase was impossible. It simply leaves the question open, and perhaps that is where the Big Bounce becomes most interesting, not as a prediction that should be accepted, but as a reminder of how incomplete our understanding of the earliest universe remains. The observable cosmos gives us an extraordinary record of its development. Yet, the closer we approach the boundary traditionally associated with the beginning, the less certain our physical descriptions become. The universe may have emerged from a singular beginning. It may have passed through a quantum transition. It may have experienced cycles extending beyond the reach of present observation. Or the true mechanism may belong to a theory that has not yet been formulated. For now, telescopes can look billions of years into the past, while mathematics can carry us even closer to the earliest moments. But somewhere beyond that boundary lies a region where observation becomes scarce and established physics begins to lose its authority. If there was a universe before ours, its traces may have been erased by the violence of the transition, or perhaps they remain hidden in the oldest light reaching us today. The cosmos gives us clues, but not yet the complete story. And somewhere between the first detectable light and the unknown physics of the primordial state lies the possibility that what we call the beginning was only another turning point. The room is quiet except for the faint hum of a computer. On a screen, a single number appears, the estimated number of human beings who have ever lived. It is an astonishing figure, measured not in thousands or millions, but in the billions. Each person occupies a tiny position within an enormous sequence stretching backward into prehistory and forward toward an unknown future. Now imagine that your own existence is also a position within that sequence. Not its beginning, not necessarily its end, simply somewhere along the line. That apparently innocent idea lies at the heart of one of the most unsettling arguments in modern philosophy of probability, the Doomsday Argument. Unlike the cosmic scenarios considered earlier, this argument does not depend upon dark energy, collapsing universes, or exotic particles. It begins with something much closer to home, the fact that you exist, and that you occupy a particular place in the chronological order of human lives. The argument emerged in its modern form during the 20th century, most famously through the work of astrophysicist Brandon Carter. In 1983, Carter presented an argument suggesting that our position among all humans who will ever live might provide statistical information about how long humanity is likely to survive. The proposition sounds almost absurdly simple, yet its implications have occupied philosophers, mathematicians, physicists, and statisticians for decades. To understand why, consider a thought experiment. Suppose humanity eventually produces a total of 1 trillion people. If every possible human birth is assigned a number according to chronological order, the first person receives number 1, another person receives number 2, and so on until the trillionth individual. Now imagine that you discover you are person number 600 billion. Would that information tell you anything about how many people will exist after you? At first, it might seem completely irrelevant, but statistical reasoning introduces a subtle complication. If you had no reason beforehand to believe that you would be born particularly early or particularly late in humanity's history, then finding yourself near the middle of the sequence could appear more probable in a population that ends relatively soon than in one that continues for an extraordinarily long time. This is the central intuition behind the Doomsday Argument. It does not claim to know the date of humanity's extinction. It does not identify a comet, war, pandemic, artificial intelligence, astronomical catastrophe, or any other specific mechanism. Instead, it asks whether the simple fact of being alive at this particular point in human history should alter our estimate of humanity's remaining lifespan. And that is where the argument becomes deeply uncomfortable. Imagine two possible futures. In the first, humanity survives for only a few more centuries, eventually disappearing after producing a comparatively modest number of people. In the second, humanity expands across the galaxy and survives for millions or even billions of years, producing an almost incomprehensible number of descendants. Under the second scenario, the number of possible future humans would vastly exceed the number who have lived so far. If you selected a human at random from the entire history of that civilization, the probability of landing on someone living extremely early in its existence would be tiny. The argument therefore suggests that our own position might constitute evidence favoring a shorter overall history. But there is an immediate problem. We are not randomly selected from all humans who will ever exist. We are observing the universe from our own particular perspective. That distinction has generated an enormous philosophical debate. The controversy centers partly on what is known as the self-sampling assumption. The idea that when reasoning about certain unknown quantities, we should treat ourselves as though we are randomly selected from an appropriate reference class of observers. The phrase sounds technical because it is. What exactly counts as the relevant group? All humans, all intelligent beings, all conscious observers, all observers capable of asking questions about their own existence? The answer matters. Suppose an alien civilization somewhere across the universe has existed for 10 million years. If we consider ourselves randomly selected from all intelligent observers in existence, our position within human history might mean something very different than if we restrict the reference class to human beings. There is no universally accepted method for deciding which reference class should govern the calculation. And without that choice, the argument can change dramatically. This is one reason the Doomsday Argument remains controversial. The room is quiet except for the faint hum of a computer. On a screen, a single number appears, the estimated number of human beings who have ever lived. It is an astonishing figure, measured not in thousands or millions, but in the billions. Each person occupies a tiny position within an enormous sequence stretching backward into prehistory and forward toward an unknown future. Now imagine that your own existence is also a position within that sequence. Not its beginning, not necessarily its end, simply somewhere along the line. That apparently innocent idea lies at the heart of one of the most unsettling arguments in modern philosophy of probability, the Doomsday Argument. Unlike the cosmic scenarios considered earlier, this argument does not depend upon dark energy, collapsing universes, or exotic particles. It begins with something much closer to home, the fact that you exist, and that you occupy a particular place in the chronological order of human lives. The argument emerged in its modern form during the 20th century, most famously through the work of astrophysicist Brandon Carter. In 1983, Carter presented an argument suggesting that our position among all humans who will ever live might provide statistical information about how long humanity is likely to survive. The proposition sounds almost absurdly simple, yet its implications have occupied philosophers, mathematicians, physicists, and statisticians for decades. To understand why, consider a thought experiment. Suppose humanity eventually produces a total of 1 trillion people. If every possible human birth is assigned a number according to chronological order, the first person receives number 1, another person receives number 2, and so on until the trillionth individual. Now imagine that you discover you are person number 600 billion. Would that information tell you anything about how many people will exist after you? At first, it might seem completely irrelevant, but statistical reasoning introduces a subtle complication. If you had no reason beforehand to believe that you would be born particularly early or particularly late in humanity's history, then finding yourself near the middle of the sequence could appear more probable in a population that ends relatively soon than in one that continues for an extraordinarily long time. This is the central intuition behind the Doomsday Argument. It does not claim to know the date of humanity's extinction. It does not identify a comet, war, pandemic, artificial intelligence, astronomical catastrophe, or any other specific mechanism. Instead, it asks whether the simple fact of being alive at this particular point in human history should alter our estimate of humanity's remaining lifespan. And that is where the argument becomes deeply uncomfortable. Imagine two possible futures. In the first, humanity survives for only a few more centuries, eventually disappearing after producing a comparatively modest number of people. In the second, humanity expands across the galaxy and survives for millions or even billions of years, producing an almost incomprehensible number of descendants. Under the second scenario, the number of possible future humans would vastly exceed the number who have lived so far. If you selected a human at random from the entire history of that civilization, the probability of landing on someone living extremely early in its existence would be tiny. The argument therefore suggests that our own position might constitute evidence favoring a shorter overall history. But there is an immediate problem. We are not randomly selected from all humans who will ever exist. We are observing the universe from our own particular perspective. That distinction has generated an enormous philosophical debate. The controversy centers partly on what is known as the self-sampling assumption. The idea that when reasoning about certain unknown quantities, we should treat ourselves as though we are randomly selected from an appropriate reference class of observers. The phrase sounds technical because it is. What exactly counts as the relevant group? All humans, all intelligent beings, all conscious observers, all observers capable of asking questions about their own existence? The answer matters. Suppose an alien civilization somewhere across the universe has existed for 10 million years. If we consider ourselves randomly selected from all intelligent observers in existence, our position within human history might mean something very different than if we restrict the reference class to human beings. There is no universally accepted method for deciding which reference class should govern the calculation. And without that choice, the argument can change dramatically. This is one reason the Doomsday Argument remains controversial. Yet despite the apparent abundance of cosmic real estate, we have no confirmed evidence of extraterrestrial technological civilizations. That silence introduces another famous problem, the Fermi paradox. If intelligent life has many opportunities to emerge, why have we not clearly encountered it? The Doomsday Argument does not solve that mystery, but together, these questions create an unsettling landscape. Perhaps, technological civilizations rarely survive long enough to spread across the stars. Perhaps the apparent silence is temporary. Perhaps intelligent life is extraordinarily rare. Or perhaps our methods of observation are still too primitive to recognize what is already there. None of these possibilities can currently be established from the Doomsday Argument alone. And this distinction is crucial. The argument is not a scientific instrument capable of calculating humanity's expiration date. It is a philosophical framework for examining what our position in time might imply under particular assumptions. Attempts to attach precise dates to humanity's future using the argument have therefore generated substantial criticism. A famous formulation by Richard Gott, sometimes called the Copernican approach to estimating longevity, uses the idea that we should not assume we are living at an unusually special point in a phenomenon's lifespan. This principle has been applied to everything from human survival to the expected duration of institutions and events. But the underlying assumption remains contestable. Are we really entitled to assume that our current moment is ordinary? Human history is full of periods that were anything but ordinary. Agriculture transformed civilization. Industrialization transformed energy use. Nuclear weapons transformed warfare. Computing transformed information. Biotechnology and artificial intelligence may alter the trajectory again. A civilization's future could depend on rare technological thresholds that have no precedent in its earlier history. If so, the past may be a poor guide to the future. Perhaps humanity is not sitting randomly along a long timeline. Perhaps we are approaching a period in which the rules of civilization are changing. Or perhaps the opposite is true. Maybe technological progress eventually encounters limits that no civilization can overcome. Maybe resources, ecological constraints, social instability, engineered pathogens, autonomous systems, or astronomical hazards place boundaries on survival. The Doomsday Argument does not identify which explanation is correct. It simply raises an uncomfortable statistical possibility. Our current position may contain information about the length of the story. Yet another objection appears. If humanity survives long enough to produce unimaginable numbers of future observers, those future observers would themselves be able to apply anthropic reasoning. They might look backward at their position and wonder why they happen to exist so late in the sequence. From their perspective, the earlier humans would appear extraordinarily unusual. This creates a strange mirror. We look toward the future and wonder whether we are early. Future beings could look toward the past and wonder whether they are late. Which perspective should dominate? Perhaps neither. Perhaps self-locating probability does not behave as intuitively as ordinary probability. That possibility has led researchers to explore alternative principles, including the self-indication assumption, which can favor worlds containing larger numbers of observers. Different assumptions can produce dramatically different expectations about humanity's future. The result is not a neat answer. It is a map of uncertainty, and perhaps that is why the Doomsday Argument continues to survive decades of criticism. It exposes a peculiar weakness in our intuition. We are accustomed to asking what will happen next, but rarely stop to consider whether the fact that we are here, now, should influence what we think is likely to happen. The argument places a mirror in front of the observer. The universe is not merely something we examine. Our existence becomes one of the clues. Whether that clue carries meaningful statistical information remains fiercely debated. There may be no hidden countdown encoded in our birth order. There may be no cosmic clock quietly measuring the remaining years of civilization. The mathematics does not establish such a conclusion. But the deeper question remains remarkably difficult to escape. If humanity eventually becomes an ancient, star-spanning civilization, today's observers will occupy only the opening fraction of an extraordinary story. If humanity ends comparatively soon, our present position may look much less surprising. Between those two possibilities lies an enormous uncertainty, and perhaps that is the most unsettling feature of the argument. Not that it predicts an ending, but that it asks whether simply being alive at this particular moment should change our expectations about one. The future remains unwritten, and probability offers no final verdict. For now, the number attached to each human life continues quietly increasing, one birth after another, while the sequence itself stretches toward an unknown horizon. Whether our place within it is meaningful evidence, or merely another illusion created by the way conscious beings experience time, is a question that mathematics alone has yet to settle. The night sky offers an illusion of simplicity. Stars appear as points of light scattered across a dark canvas, while galaxies remain so distant that their enormous scale becomes almost impossible to feel. Yet, hidden behind that quiet appearance is a remarkable fact. The universe possesses physical properties that allow complex structures to exist at all. Gravity has a particular strength. The electromagnetic force operates within a particular range. The masses of elementary particles fall within specific values. The universe contains a particular balance between matter and radiation. Even the expansion of space follows parameters that have shaped everything from galaxies to chemistry. Change some of these conditions substantially, and the cosmos could become radically different. Stars might never ignite. Galaxies might fail to form. Atoms might not remain stable. Complex chemistry might never emerge. There might be no planets, no oceans, no organisms, and no observers capable of looking into the night sky. This observation sits at the heart of one of the most philosophically challenging ideas in modern cosmology: the Anthropic Principle. The concept does not begin by claiming that the universe was designed for life. It begins with something far more modest. We are here. And because we are here, any universe we observe must possess conditions compatible with our existence. That statement sounds almost obvious. Yet, once physicists began examining the numerical structure of fundamental laws, the implications became considerably more subtle. The story reaches back through several strands of 20th century physics and cosmology, eventually taking a more recognizable form with Brandon Carter, who introduced the term Anthropic Principle in 1973. Carter distinguished between different versions of the principle, particularly what became known as the weak anthropic principle and the strong anthropic principle. The weak version is relatively restrained. It states, essentially, that our observations of the universe are constrained by the requirement that the universe must be capable of producing observers like us. That sounds simple because it is. A fish studying its environment would inevitably find itself in water. A creature capable of existing only under certain atmospheric conditions would never observe a planet where those conditions were absent. The observer cannot sample every possible environment. The observer can only exist where observation is possible. Applied to cosmology, this creates an important selection effect. Suppose the universe could have possessed many different physical conditions. Most might have been hostile to complex life. We should not be surprised to find ourselves in one of the rare environments where observers can emerge, because an observer could not find itself anywhere else. The mystery begins when scientists discover just how sensitive some cosmic structures appear to be to the values of fundamental parameters. Consider stars. Stars are not merely bright objects decorating the sky. They are enormous nuclear furnaces whose interiors transform lighter elements into heavier ones. Through stellar evolution, elements such as carbon, oxygen, and other heavier atoms become available for later generations of stars, planets, and eventually living systems. The existence of long-lived stars therefore depends on the laws of physics, allowing stable nuclear fusion. Change the relevant parameters enough, and stellar evolution could look entirely different. A universe dominated by short-lived stars would offer far less opportunity for complex chemistry and biological evolution. Then there is carbon. Carbon possesses chemical properties that make it extraordinarily versatile. Its ability to form stable bonds with itself and with other elements allows an immense variety of molecules to exist. That does not prove that carbon-based life was inevitable. but it demonstrates how deeply biology depends upon the underlying structure of physics and chemistry. The universe does not merely contain life. Life depends upon a chain of physical possibilities extending all the way down to the behavior of elementary particles. One of the most frequently discussed examples involves the cosmological constant, a parameter associated with the energy density of empty space. Observations indicate that the expansion of the universe is accelerating, and the simplest cosmological model attributes this acceleration to dark energy behaving approximately like a cosmological constant. The observed value is extraordinarily small compared with some theoretical expectations. If the effective vacuum energy were much larger and positive, cosmic expansion could become so rapid that matter would struggle to gather into galaxies and other large structures. If it were sufficiently negative, gravitational collapse could potentially dominate on cosmic scales. Some range of values appears more hospitable to the formation of complex structures. This apparent sensitivity has become one of the central reasons the Anthropic Principle continues to appear in discussions of fundamental physics. Why do the constants of nature have the values they do? Are they determined by a deeper theory that we have not yet discovered? Are they accidental? Could there be many physically possible universes with different parameters, with observers naturally finding themselves only in the small subset capable of supporting complexity? Or does the apparent fine-tuning point towards something more fundamental? These questions have no universally accepted answer. The phrase fine-tuning itself requires caution. It does not necessarily mean that someone tuned the universe deliberately. In physics, the term often refers to situations in which a system's behavior appears unusually sensitive to the precise values of certain parameters. The interpretation is where the controversy begins. One possible explanation is that a deeper physical theory will eventually show that the parameters could not have been otherwise. Perhaps what looks like coincidence today will become mathematically necessary tomorrow. Another possibility involves the multiverse. If reality contains an enormous ensemble of universes, or causally disconnected regions, with different physical properties, then observers would naturally find themselves in a region compatible with life. A universe unable to form galaxies would contain no astronomers wondering why its constants were unsuitable. A universe capable of producing stars, chemistry, and biology could eventually produce observers who notice the apparent coincidence. This is sometimes called an anthropic explanation. But the multiverse introduces a new difficulty. How can such universes be tested? If other cosmic regions are permanently inaccessible, direct observation may be impossible. Scientists therefore debate whether multiverse scenarios can generate testable predictions, or whether they risk becoming explanations that are difficult to distinguish from philosophical speculation. The debate is not merely about whether multiple universes exist. It is about what should count as a scientific explanation. And that question reaches deep into the philosophy of science. Suppose a theory predicts that countless universes exist, most hostile to life, while a small fraction permit observers. Discovering ourselves inside one of those hospitable regions would then be expected. But does that actually explain why our universe has its particular properties? Or does it simply move the question backward? Why does the multiverse possess the underlying rules that generate those universes? Why do those rules permit complexity? Why is there a reality capable of producing observers at all? Anthropic reasoning can illuminate one level of the puzzle while leaving another untouched. The stronger forms of the principle take the discussion even further. The strong anthropic principle has been interpreted in several ways, but broadly, it considers the possibility that the universe must possess properties allowing intelligent life to develop. Some formulations sound almost teleological, as though the cosmos were somehow required to produce observers. That interpretation is controversial. A physical principle does not automatically imply purpose. The fact that observers can exist in a particular universe does not demonstrate that the universe was created for observers. Yet, the language surrounding the strong anthropic principle has sometimes encouraged precisely that interpretation. This is where scientific reasoning meets philosophical territory. There is also a more subtle idea known as the participatory anthropic principle, associated particularly with physicist John Archibald Wheeler. Wheeler explored the possibility that observers might play a fundamental role in defining physical reality, drawing inspiration from quantum mechanics and the relationship between measurement and physical states. This does not mean that human minds magically create galaxies, nor does it establish that consciousness controls the universe. Rather, Wheeler's ideas raised deeper questions about whether observation and physical reality are more intimately connected than classical physics suggests. Quantum mechanics already presents an unusual relationship between measurement and the description of physical systems. But extending that relationship to the entire universe remains highly speculative. The question becomes almost circular. Could a universe exist without observers? If no observer were present, would physical reality still possess the same meaning? Most physicists would distinguish the existence of physical processes from our ability to observe them. Stars formed long before humans existed. Galaxies collided before Earth was born. Nothing about the anthropic principle requires a conscious observer to create those events. Its central insight is about selection. Only a universe compatible with observers can be observed by observers. That distinction sounds small. It is enormous. Imagine an astronomer arriving at a planet and discovering that its atmosphere contains exactly the chemical mixture required for life. The discovery would be remarkable. But if the astronomer had been born on that planet, the observation would no longer be surprising in the same way. The observer's existence would already constrain the environment being observed. Cosmology confronts a similar problem on a vastly larger scale. We cannot step outside the universe and examine it as an ordinary object. There is no external laboratory in which alternative universes can be placed side by side. Our measurements come from inside the system. Our existence comes from inside the system. Even our questions are products of the physical processes we are trying to understand. That makes the universe an unusual scientific subject. There is no detached observer standing beyond it. The observer is part of the evidence. This connects the anthropic principle directly to the Doomsday Argument discussed earlier. The Doomsday Argument asks whether our particular position among human observers provides information about humanity's future. The Anthropic Principle asks how the existence of observers constrains what can be observed in the first place. Both involve self-location. Both force science to confront the strange fact that the observer cannot simply be removed from the equation. But the implications extend beyond human beings. Consider a hypothetical universe with slightly different physical constants. Perhaps gravity is too strong for long-lived stars. Perhaps electromagnetic interactions prevent complex chemistry. Perhaps the universe expands so quickly that matter never gathers into galaxies. Such a universe could be mathematically consistent. It might possess space, time, particles, and physical laws. But there would be no astronomers there to ask why the universe is lifeless. This creates a powerful selection effect. We should expect our observations to come from a universe capable of producing observers. But how much does that expectation actually explain? That remains one of the central unresolved issues. Some physicists view anthropic reasoning as a useful way to understand otherwise puzzling observations, particularly when combined with broader theoretical frameworks such as inflation and possible multiverse scenarios. Others remain skeptical, arguing that physics should seek deeper mechanisms rather than accept observer selection as an explanation for fundamental constants. Both positions have serious arguments behind them. The disagreement reveals something important. Science is not only a process of collecting measurements, it is also a process of deciding what constitutes a satisfactory explanation. If the universe appears finely balanced for complexity, one scientist may search for a hidden law forcing those values. Another may investigate whether many universes could naturally produce a wide range of values. A third may argue that the apparent fine-tuning is partly a consequence of incomplete understanding. At present, none of these possibilities has settled the matter. And there are still more profound questions. Why does the universe contain mathematical regularities at all? Why do its laws permit stable matter? Why does the universe possess an arrow of time? Why did conditions emerge that allowed stars, planets, chemistry, and eventually conscious beings? The Anthropic Principle does not answer all of these questions. Perhaps it was never meant to. Its power lies partly in the way it changes the question. Instead of asking only, why does the universe have these particular properties, it asks, what properties could a universe have if observers are going to exist within it? That is a narrower question, but also a more unsettling one. Because once the observer enters the equation, the universe begins to look different. The apparent coincidence of physical constants may be evidence of deeper laws. It may reflect selection among many possible cosmic environments. It may arise from mechanisms we have not discovered. Or perhaps our intuition about what counts as unlikely is itself inadequate when applied to the universe as a whole. There is one final complication. We know of only one universe. Every statement about how typical or unusual our cosmos is ultimately rests upon a single observed example. We cannot survey an inventory of universes and calculate where ours ranks. We cannot compare its constants with those of neighboring realities. We cannot look beyond the observable horizon to determine whether the same physical conditions extend indefinitely. Our sample size, at least for now, is 1. And perhaps that is why the Anthropic Principle remains so difficult to classify. It sits at an unusual border between cosmology, probability, philosophy, and the limits of observation. It does not reveal a hidden architect. It does not prove a multiverse. It does not demonstrate that consciousness created reality. Instead, it places a quiet constraint upon the entire discussion. Whatever the ultimate nature of reality may be, we are encountering it from a position that was made possible by the very laws we are trying to understand. The night sky remains unchanged above us. Stars continue burning across distances measured in light years. Galaxies continue forming and colliding. Particles obey rules established long before any human mind could describe them. And somewhere within that immense structure, conscious observers have appeared, looked outward, and begun asking why the universe permits their existence. Whether that fact is merely a consequence of selection, a clue to deeper physics, or a sign that our current picture of reality is missing, something fundamental remains unresolved. Perhaps the most difficult mystery is not why the universe looks the way it does. Perhaps it is why there is a universe whose laws allow anything capable of noticing at all. Far beyond the nearest stars, where light itself can be trapped by gravity, there are regions of space-time so extreme that our ordinary understanding of cause and effect begins to strain. A black hole may appear deceptively simple from a distance, a dark center surrounded by a glowing disk of superheated gas, with streams of matter spiraling inward at extraordinary speeds. Yet, the darkness surrounding a black hole conceals a question that reaches far deeper than astronomy. What happens to information when something falls inside? The question emerged from a collision between two of the most successful theories in modern physics. General relativity describes gravity on cosmic scales, explaining how massive objects curve space-time. Quantum mechanics governs matter and energy at microscopic scales, where particles behave according to probabilities in quantum states. Each theory has survived extraordinary tests. Together, however, they create a problem. Black holes sit precisely where their domains overlap. The story begins with the prediction of black holes in general relativity. In 1915, Albert Einstein published his theory of general relativity, describing gravity not as an ordinary force, but as the curvature of space-time produced by matter and energy. Only months later, Karl Schwarzschild found an exact solution to Einstein's equations describing the gravitational field surrounding a spherical mass. The mathematics contained a remarkable boundary, a radius beyond which an object could become so compact that escape would require a speed greater than that of light. This boundary became known as the event horizon. For decades, black holes remained largely theoretical objects. The idea was mathematically compelling, but direct observational evidence was difficult to obtain. That changed gradually. Astronomers discovered stars orbiting invisible massive objects. X-ray observations revealed compact objects consuming matter from nearby companions. Gravitational wave detectors later observed ripples produced by merging black holes. In 2019, the Event Horizon Telescope collaboration produced the first image of the shadow of a black hole in the center of the galaxy Messier 87. A few years later, the collaboration released an image of the black hole at the center of our own galaxy, Sagittarius, a star. Black holes were no longer merely mathematical curiosities. They had become observable features of the universe. But the deeper problem was still waiting. In the 1970s, physicist Stephen Hawking showed that when quantum effects are considered near a black hole's event horizon, the object should emit thermal radiation. This was revolutionary. A black hole was not completely black. It could slowly lose energy, and if the process continued long enough, the black hole could eventually evaporate. At first, the result seemed like an extraordinary prediction connecting quantum theory, gravity, and thermodynamics. Then, physicists noticed something disturbing. If Hawking radiation is purely thermal, it appears to depend only on broad properties of the black hole, such as its mass, charge, and angular momentum. The detailed information about whatever entered the black hole seems to disappear. A book falls inward. A cloud of particles follows. A spacecraft crosses the horizon. A star collapses. According to the simplest interpretation of Hawking's calculation, the radiation emitted later would not preserve the complete microscopic information describing those objects. Eventually, the black hole could evaporate entirely. What remains? A cloud of thermal radiation containing no obvious record of the original state. That creates the paradox. Quantum mechanics strongly suggests that information cannot simply be destroyed by physical evolution. The precise mathematical formulation depends on the framework being used, but the principle is deeply embedded in quantum theory. If the initial state of a quantum system contains information, its later state should retain that information in some form. Black hole evaporation appears to threaten that principle. General relativity seems to permit information to disappear behind an event horizon. Quantum mechanics resists the idea. Something has to give. This became known as the black hole information paradox. The paradox is not merely about whether we can retrieve a message from a black hole. It is more fundamental. Suppose a quantum state falls into a black hole. If the black hole eventually evaporates and disappears, what happened to the information contained in that original state? Was it destroyed? Was it somehow encoded in the radiation? Did it remain hidden in a remnant? Or does our understanding of space-time break down before the question can even be formulated in its original terms? For years, physicists explored radically different possibilities. One proposal suggested that black holes might leave behind tiny, stable remnants containing the information accumulated during their lifetimes. But such remnants introduce their own theoretical difficulties. If an enormous amount of information can be stored inside an extremely small object, the number of possible internal states becomes enormous. This can create problems involving quantum gravity and the consistency of the theory. Another possibility is that Hawking radiation is not truly featureless. Perhaps the radiation carries extremely subtle correlations. To an observer examining individual particles, the radiation might appear almost thermal. But when the complete quantum state is considered, tiny relationships between emitted particles could preserve information about what fell into the black hole. This possibility became increasingly influential. The paradox then shifts. Information may not disappear. It may simply become extraordinarily scrambled. Imagine taking an intricate manuscript and shredding it into microscopic fragments, scattering those fragments across an enormous landscape. The original arrangement would be almost impossible to reconstruct in practice, yet the information would not necessarily have been fundamentally erased. Black hole evaporation could be something like that, but at a far deeper quantum level. The information might survive in correlations spread across the outgoing radiation. The challenge is demonstrating exactly how. Another extraordinary idea emerged from the study of black hole thermodynamics. Black holes appear to possess entropy. In the 1970s, Jacob Bekenstein proposed that the entropy of a black hole is related not to its volume, but to the area of its event horizon. Hawking's calculations supported this connection. The result was astonishing. A black hole's entropy is proportional to the area of its horizon. This suggested that the information content of a region of space might somehow be encoded on its boundary. That possibility eventually contributed to the development of the holographic principle. The name comes from the analogy with a hologram, where information describing a three-dimensional image can be encoded on a two-dimensional surface. The idea does not mean that the universe is literally a projection in the everyday sense. Rather, it suggests that a gravitational theory in a given volume may have an equivalent description using degrees of freedom associated with a lower dimensional boundary. This concept became especially concrete through the ADS/CFT correspondence proposed by Juan Maldacena in 1997, which relates a gravitational theory in a higher dimensional spacetime to a quantum field theory defined on its lower dimensional boundary. The correspondence provided powerful theoretical evidence that gravitational systems can encode information in ways that differ dramatically from ordinary intuition. Black holes became laboratories for studying this strange relationship. Yet another proposal took a more dramatic form. Could information remain encoded on the event horizon itself? Some physicists developed ideas involving black hole complementarity, suggesting that different observers might describe the fate of information differently without encountering a direct contradiction. For an observer falling toward a sufficiently large black hole, crossing the event horizon might appear locally uneventful. For an observer remaining far away, information could appear to be absorbed and eventually encoded in radiation associated with the horizon. Both descriptions might be valid within their respective observational frameworks. But then came a new challenge. The firewall paradox proposed by Almheri, Marolf, Polchinski, and Sully in 2012 argued that certain assumptions about quantum entanglement, information preservation, and the smoothness of the event horizon could be mutually incompatible. One possible consequence was deeply unsettling. Perhaps the event horizon is not the gentle boundary predicted by classical general relativity. Perhaps an infalling observer would encounter an intense region of high-energy physics, a firewall, instead of crossing smoothly. The idea remains controversial. It was not proposed because physicists had observed literal walls of fire surrounding black holes. It emerged because several apparently reasonable principles seemed difficult to maintain simultaneously. This illustrates the unusual character of the information paradox. The mystery is not based on a missing observation. It arises because our best theories appear to disagree about what reality is allowed to do, and the deeper researchers look, the more intriguing the problem becomes. Quantum entanglement appears to play a central role. Particles can share quantum states in ways that connect their measurable properties even when separated by enormous distances. In modern approaches to quantum gravity, entanglement may be far more than a peculiar feature of microscopic systems. It may be related to the structure of spacetime itself. Some theoretical work suggests that geometric connections could emerge from patterns of quantum entanglement. If so, the information paradox may not merely concern what happens inside black holes. It could be revealing something fundamental about why spacetime exists in the form we experience. Recent developments have added another layer. Calculations involving quantum gravitational effects and so-called islands have reproduced an expected pattern for the entropy of Hawking radiation, including the appearance of the Page curve. This has provided important theoretical progress toward understanding how information might remain consistent with quantum mechanics during black hole evaporation. But an elegant calculation is not the same as a complete physical explanation. Researchers are still investigating what these results mean in a fully realistic theory of quantum gravity. The black hole information problem therefore remains a crossroads. General relativity tells us that the event horizon is a feature of spacetime geometry. Quantum theory tells us that information should behave in a fundamentally reversible way under ordinary unitary evolution. Thermodynamics tells us that black holes possess entropy and temperature. Holography suggests that gravitational information may be encoded in unexpected ways. Quantum entanglement appears increasingly connected to the architecture of spacetime. And yet, there is still no universally accepted, experimentally confirmed theory explaining the entire picture. Perhaps information truly escapes through subtle correlations in Hawking radiation. Perhaps the interior of a black hole is connected to the exterior in ways that classical spacetime conceals. Perhaps the horizon has a fundamentally quantum structure. Perhaps our concept of locality, the idea that objects possess properties only within their immediate surroundings, must be reconsidered. Or perhaps the resolution requires a theory so different from our current frameworks that the familiar language of inside and outside will eventually seem inadequate. For now, black holes continue to form across the universe. Massive stars collapse. Galaxies merge. Supermassive black holes grow at the centers of galaxies. Gravitational waves ripple outward through spacetime. From Earth, these objects appear distant and silent, their horizons marking boundaries beyond which ordinary signals cannot return. Yet, they may be doing something far more important than simply consuming matter. They may be testing the foundations of physical law. The information paradox asks whether the universe can truly forget. If information survives, where is it stored? If it escapes through radiation, how is that information encoded? If the horizon itself contains the answer, what does that imply about the nature of space? And if quantum gravity eventually dissolves the distinction between the interior and exterior of a black hole, what becomes of the very idea that information was ever trapped? We do not yet have a final answer. What we have instead is an extraordinary trail of clues: horizon entropy, Hawking radiation, quantum entanglement, holography, black hole complementarity, firewalls, and the page curve. Each has brought the mystery into sharper focus without fully closing it. Somewhere beyond the luminous disk surrounding a distant black hole, matter continues crossing a boundary from which no ordinary light returns. Whether the information carried by that matter is destroyed, transformed, hidden, or written into the fabric of space-time itself remains one of the deepest unresolved questions in theoretical physics. And perhaps the darkness of a black hole is not frightening because nothing escapes it, but because the answer to what happens inside may force us to reconsider what information, reality, and space itself truly mean. Inside a laboratory, the scene can appear almost disappointingly ordinary. A vacuum chamber rests beneath carefully controlled instruments. Lasers pass through optical components. Detectors wait for individual flashes of light. Nothing appears dramatic. Yet, at this microscopic scale, nature behaves according to rules that seem profoundly different from the world of tables, planets, and falling objects. A particle can occupy a combination of possible states. Its location may not possess one definite value. Its behavior can be described by a wave function containing several possibilities at once. Then, a measurement is made. The detector records one result. The ambiguity disappears from what we observe. But what exactly happened? That deceptively simple question lies at the center of one of quantum theory's oldest and most persistent conceptual difficulties: the measurement problem. The previous section considered what happens when information encounters the extreme geometry of a black hole. Here, the mystery becomes smaller in scale, but no less profound. Instead of asking whether information can escape from a cosmic horizon, we are asking something almost embarrassingly basic. How does a quantum possibility become a definite event? Quantum mechanics emerged during the early 20th century through a series of discoveries that overturned classical expectations. Max Planck introduced the idea of quantized energy in 1900. Albert Einstein used quantization to explain the photoelectric effect in 1905. Niels Bohr developed an early quantum model of the atom. Later, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others helped construct the mathematical framework of modern quantum theory. The results were extraordinarily successful. Quantum mechanics correctly predicts the behavior of atoms, molecules, semiconductors, lasers, nuclear systems, and countless technologies that shape modern life. Its equations work. The conceptual picture remains unsettled. One of the central mathematical objects in quantum mechanics is the wave function. The wave function does not necessarily describe a tiny object moving through space like a miniature billiard ball. Instead, it encodes the quantum state of a system and allows physicists to calculate the probabilities of different measurement outcomes. Consider an electron prepared in a state that allows two possible measurement results. Before measurement, quantum mechanics can represent the system as a superposition of those possibilities. This is not simply a statement that we personally lack knowledge about which result will occur. That distinction is crucial. A classical coin hidden beneath a cup has already landed heads or tails, even though we do not know which. A quantum system can behave differently. Experiments repeatedly demonstrate interference effects that arise when quantum alternatives coexist coherently. The famous double-slit experiment provides one of the clearest demonstrations. Send individual particles toward two narrow openings and record where they arrive on a screen. Over time, an interference pattern can emerge, even when particles are sent through the apparatus one at a time. The result suggests that quantum amplitudes associated with different paths combine in a way that has no straightforward classical equivalent. Yet, when the experiment is arranged so that which path information becomes available, the interference disappears. Something about measurement matters. But what? The traditional textbook description often introduces a distinction between two types of evolution. When a quantum system is not being measured, its wave function evolves smoothly according to the Schrödinger equation. That evolution is continuous and deterministic. But when a measurement occurs, the theory is commonly described as undergoing collapse. Instead of retaining multiple possible outcomes, the wave function appears to reduce to one definite result. The electron is detected here. The photon arrives there. The detector displays one number. The quantum possibilities become an observed reality. This creates the central tension. If the Schrödinger equation describes physical systems universally, should it also describe measuring devices? A detector is made of atoms. An observer is made of atoms. A laboratory is made of quantum matter. So why should the mathematical rules suddenly change when a measurement takes place? Where exactly is the boundary? Is it between a particle and a detector? Between a detector and a human observer? Between microscopic and macroscopic systems? Or is there no fundamental boundary at all? The question has never received a universally accepted answer. Niels Bohr and Werner Heisenberg developed what later became known broadly as the Copenhagen interpretation, although there was never a single, perfectly unified Copenhagen doctrine. This family of views emphasizes the role of measurement and the limits of classical descriptions when applied to quantum systems. Bohr argued that experimental arrangements are essential to the meaning of quantum phenomena. Certain properties cannot simply be assigned definite classical values independent of the measurement context. The interpretation became enormously influential. It also left generations of physicists debating what the formalism actually says about reality. Albert Einstein was deeply uncomfortable with some implications of quantum mechanics, particularly the idea that nature might be fundamentally probabilistic. His famous disagreements with Bohr were not simply philosophical arguments between two personalities. They represented a deeper conflict over what a physical theory should describe. Einstein believed that a satisfactory theory should provide a more complete account of reality. Bohr defended the quantum framework's empirical success and emphasized the role of experimental conditions. The debate became one of the defining intellectual confrontations of 20th century physics. Einstein's famous thought experiments with quantum systems eventually contributed to the development of what is now known as Bell's theorem. In 1964, physicist John Bell showed that no theory satisfying certain assumptions about locality and hidden variables could reproduce all the predictions of quantum mechanics. Experiments conducted decades later repeatedly found violations of Bell inequalities consistent with quantum predictions. These results did not settle every philosophical question about quantum mechanics, but they sharply constrained a large class of classical hidden variable explanations. The mystery therefore survived in a more refined form. If quantum mechanics is correct, what does its wave function represent? Is it a physical object, a mathematical description of our knowledge, a catalog of possible outcomes, or something more fundamental? Different interpretations answer differently. The many worlds interpretation, associated with Hugh Everett's work in the 1950s, removes wave function collapse entirely. According to this approach, the universal wave function always evolves according to quantum mechanics. When a measurement occurs, different possible outcomes become correlated with different states of the observer and environment. What appears to be a single outcome from one observer's perspective corresponds to branching structures within the quantum state. There is no special moment when nature chooses one possibility. All allowed outcomes remain represented in the overall state. The interpretation is mathematically serious and has attracted many researchers. Yet, it carries an extraordinary conceptual consequence. If every quantum possibility is realized in some branch of the universal wave function, then the apparent uniqueness of our observed reality becomes a feature of our particular branch rather than evidence that alternatives were physically eliminated. Other approaches take a different route. Objective collapse theories propose that wave function collapse is a genuine physical process rather than merely an update of information. Models such as the Ghirardi-Rimini-Weber framework introduce spontaneous collapses that become increasingly significant for large systems. In such theories, quantum superpositions are real but unstable under certain conditions. A sufficiently large system would naturally settle into a definite state. This offers a possible explanation for why everyday objects do not normally appear in obvious macroscopic superpositions. It also creates something experimentally interesting. If collapse is a real physical phenomenon, perhaps extremely sensitive experiments could detect deviations from ordinary quantum mechanics. Researchers have searched for such effects. So far, no confirmed observation has established an objective collapse mechanism. Another major development is decoherence. When a quantum system interacts with its environment, information about its state becomes distributed into enormous numbers of surrounding degrees of freedom. Interference between alternatives can become effectively inaccessible. The system begins behaving as though it has selected a classical outcome. Decoherence is a powerful and experimentally supported phenomenon. It helps explain why quantum behavior becomes difficult to observe in large, environmentally connected systems. But there is an important distinction. Decoherence does not by itself explain why one specific outcome is experienced. It explains why interference between alternatives becomes suppressed. The deeper question of why a particular result appears can remain. This is sometimes called the preferred basis problem, or, more broadly, part of the measurement problem. Why do certain macroscopic states become stable and definite while quantum possibilities disappear from our ordinary experience? The environment appears to play a major role, but whether decoherence alone provides a complete solution remains debated. Then, there are interpretations in which measurement does not require consciousness at all. This is worth emphasizing because popular discussions sometimes suggest that human awareness somehow creates physical reality. Quantum mechanics does not establish such a claim. There is no experimental evidence demonstrating that consciousness causes wave function collapse. Some historical interpretations and philosophical proposals have explored relationships between observation and reality, but modern quantum physics does not require a conscious mind to trigger every measurement. A detector can interact with a quantum system. A photographic plate can record a particle. A molecule can become entangled with its environment. The physical interaction itself is enough to produce measurable consequences. The mystery lies deeper than human perception. Perhaps the most unsettling aspect of the measurement problem is that the mathematics is often clearer than the ontology. Physicists know how to calculate probabilities. They know how quantum states evolve. They can predict experimental results to extraordinary precision. But asking what the mathematical objects are leads into territory where consensus disappears. Is the wave function physically real? If it is, why does one outcome appear definite? If it is not, what exactly is evolving? And if collapse is merely an update in knowledge, whose knowledge is changing when a detector records a result? The questions become even more difficult when the entire universe is treated quantum mechanically. There is no external laboratory surrounding the universe. There is no observer standing outside space-time. If quantum mechanics is fundamental, then the universe itself should possess a quantum state. But who, or what, performs the measurement? Cosmologists studying the early universe confront versions of this problem when attempting to describe primordial quantum fluctuations that later became the seeds of galaxies. Those fluctuations were not measured by an external observer at the moment they occurred. yet their consequences appear across the large-scale structure of the cosmos. This suggests that the traditional picture of a conscious observer watching a quantum system is far too narrow. Measurement may need to be understood as a physical process involving interactions, information, entanglement, and the emergence of classical behavior. But whether that fully resolves the original puzzle remains open. There are also interpretations based on relational quantum mechanics, where the properties of a system are understood relative to other physical systems. There are information-centered approaches in which the quantum state represents information or expectations rather than an objective physical wave. There are hidden variable theories, including Bohmian mechanics, where particles possess definite positions guided by a quantum wave. Each framework preserves different intuitions while surrendering others. The remarkable fact is that several interpretations can reproduce the same experimental predictions. That creates a peculiar situation. Physics may tell us what nature does while remaining ambiguous about what nature ultimately is. Perhaps future experiments will reveal tiny differences between competing theories. Perhaps increasingly precise tests of quantum behavior at larger scales will expose new physics. Perhaps gravity itself will prove essential to understanding why classical reality emerges. Or perhaps the measurement problem will survive because it is not a problem with the equations at all, but with our insistence that the equations must correspond to one particular picture of reality. The laboratory remains quiet. A detector clicks. A number appears on a screen. The experiment is repeated, and the prediction succeeds again. From the outside, nothing seems mysterious. Yet, behind that single recorded result lies a conceptual divide that has endured for generations. A quantum system can be represented by several possible outcomes. A measurement gives us one. Between those two descriptions lies a gap that physics has not completely closed. Maybe the missing piece is hidden in the structure of quantum information. Maybe it lies within the relationship between matter and consciousness. Maybe there is no collapse at all, and the appearance of a single reality is an emergent feature of a much larger quantum state. Or perhaps the question itself is asking for a classical answer from a world that does not operate classically. The instruments continue to improve. The experiments become more delicate. The equations become more precise. Yet, when the detector finally clicks, one mystery remains quietly attached to that tiny event. Why this result and not another? The measurement has been made. The explanation is still waiting. A pendulum swings inside a sealed chamber, tracing the same narrow arc through the air. Its motion appears ordinary, almost hypnotic. Every oscillation carries the system through another arrangement of position and momentum, while countless invisible particles in the surrounding environment follow their own complicated trajectories. Now imagine a perfectly isolated physical system containing an enormous number of particles. Give it enough time. Not years, not millions of years. A span so vast that ordinary measures of history become meaningless. Under certain conditions, mathematics suggests that the system could eventually return arbitrarily close to a state it occupied long ago. The idea sounds almost like a cosmic memory. It is known as the Poincaré recurrence theorem. The theorem was formulated by the French mathematician Henri Poincaré in the late 19th century, during his work on the difficult mathematical problem of celestial mechanics. At the time, scientists were attempting to understand whether the long-term motion of planets and other gravitational systems could remain stable. Newtonian mechanics had provided an extraordinarily powerful framework for describing motion. But long-term behavior was another matter. A system governed by deterministic equations could still behave in ways that were extremely difficult to predict after enormous periods of time. Poincaré discovered something profound while studying these dynamical systems. Under specific mathematical conditions, a bounded system that evolves according to appropriate deterministic laws will eventually return arbitrarily close to its initial state. Not necessarily exactly, not necessarily within any practical period, but as close as desired, given enough time. The distinction is essential. The theorem does not say that every object in the universe will eventually return to exactly the same arrangement. It applies only under particular assumptions, including that the system occupies a finite region of phase space and evolves in a way that preserves the relevant measure. Those conditions are highly restrictive, yet the conceptual consequence is remarkable. A system can wander through an enormous number of possible configurations without permanently escaping its accessible state space. Given sufficient time, it can revisit regions it occupied before. Imagine a box containing a gas. At first, the molecules are concentrated in one corner. Release them. They spread throughout the container, moving in every direction and colliding countless times. Eventually, the gas reaches a state that appears uniform. Classical thermodynamics tells us that such a configuration is overwhelmingly more probable than the original concentrated arrangement. But the microscopic laws governing the molecules are, to a remarkable approximation, reversible. The molecules do not possess a built-in memory of thermodynamic time. If the system were perfectly isolated and allowed to evolve for an unimaginably long duration, the Poincaré recurrence theorem suggests that the particles could eventually approach a configuration resembling their earlier arrangement. The gas could, in principle, gather again. The room could become temporarily ordered. A microscopic history could almost repeat itself. The difficulty is the timescale. For a macroscopic system containing something like the number of particles found in an ordinary room, recurrence times can be so immense that they dwarf the age of the universe by an incomprehensible margin. The theorem, therefore, does not imply that your coffee will spontaneously return to its original state tomorrow. It does not provide a practical mechanism for reversing entropy. It describes a mathematical property of certain dynamical systems operating over extraordinary periods. Yet, its relationship with thermodynamics has fascinated scientists ever since. The second law of thermodynamics tells us that entropy tends to increase in an isolated system. Ice melts, perfume disperses, hot objects cool. A broken glass does not spontaneously reconstruct itself on the floor. At the macroscopic level, these processes have a clear direction. Time appears to have an arrow. But microscopic mechanics is far less directional. The fundamental equations of classical mechanics generally allow trajectories to be reversed. If every particle's position and velocity were reversed with perfect precision, the system could, in principle, retrace its path. So, where does irreversibility come from? The recurrence theorem sharpened this old puzzle. If a closed mechanical system eventually returns near previous states, how can entropy continue increasing indefinitely? The answer lies partly in probability. A low entropy state occupies an extraordinarily tiny region of the possible microscopic configurations of a system. A high entropy state corresponds to an enormous number of microscopic arrangements. A gas filling a room uniformly can be realized in an immense number of microscopic ways. A gas gathered neatly into one corner can be realized in comparatively few. Nothing in the microscopic laws necessarily forbids the low entropy arrangement. It is simply fantastically improbable. The recurrence theorem, therefore, does not contradict thermodynamics in the straightforward way it might first appear. Instead, it highlights a distinction between mathematical possibility and practical probability. Given an immense enough amount of time, an extraordinary fluctuation can become possible. But possible does not mean likely on any meaningful human timescale. This distinction becomes even more intriguing when the theorem is considered alongside the modern understanding of statistical mechanics. Ludwig Boltzmann, whose work was central to the development of statistical thermodynamics, wrestled with similar questions. If microscopic laws are reversible, why does entropy appear to increase toward the future rather than decrease just as naturally toward the past? One possible answer is that the universe began in an extraordinarily low entropy state. If so, the arrow of time may be less a fundamental feature of every microscopic law and more a consequence of the universe's unusual initial conditions. The recurrence theorem adds another layer. If a finite, isolated system can eventually revisit earlier states, then the apparent direction of time may not continue forever in the simple way we experience it. The system could wander through its available configurations, approaching old arrangements again and again. But how does this apply to the universe? That question requires caution. The observable universe is not simply a sealed box containing a fixed number of particles moving through a finite region under classical mechanics. Cosmic expansion, general relativity, quantum fields, gravity, dark energy, horizons, and the possibility of an effectively infinite spatial extent complicate the picture enormously. The original Poincaré theorem does not automatically apply to the universe as a whole. Still, cosmologists and theoretical physicists have explored related ideas. If a universe or a particular cosmological region possesses the necessary finite phase space structure and evolves for sufficiently long periods, recurrence-like behavior can arise in certain theoretical models. This possibility becomes especially interesting in cosmologies involving a long-lived de Sitter-like state, where accelerated expansion continues and the accessible region associated with an observer can possess finite entropy. Under certain assumptions, extraordinarily rare fluctuations could occur over immense timescales. A universe that appears to settle into a nearly empty state might, in principle, experience an exceptionally unlikely fluctuation. And this leads to one of the strangest ideas associated with recurrence. If a physical system has enough time, perhaps not only simple configurations but extraordinarily complex ones could arise as statistical fluctuations. Could a brain-like structure emerge spontaneously from random fluctuations? The theoretical object proposed in this context is known as a Boltzmann brain. The idea is not a claim that such brains actually exist. It is a problem used to test certain cosmological models. Suppose a universe remains in a high entropy state for an extraordinarily long time. If fluctuations are allowed, a rare fluctuation producing a functioning observer might be vastly more probable than a fluctuation reconstructing an entire low-entropy universe with billions of galaxies. If so, a theory might predict that observers like us should overwhelmingly be short-lived fluctuations, rather than inhabitants of a vast, orderly cosmos. That conclusion conflicts with our observations. We see a universe with a long cosmic history. We observe galaxies, stars, planetary systems, and a detailed thermal background consistent with a hot, early universe. We possess memories of events extending through years and generations. A cosmological model dominated by Boltzmann brains would therefore face a serious problem. The issue is not evidence that such entities exist. It is evidence that certain models may produce an unacceptable prediction about what typical observers should experience. Recurrence thus becomes more than a mathematical curiosity. It can serve as a test of the assumptions built into theories of the universe. If a cosmological model predicts that, after unimaginably long periods, random fluctuations should produce vastly more observer-like configurations than ordinary cosmic evolution produces observers, physicists may question whether the model is describing reality correctly. There is something almost poetic about the underlying principle. Given enough time, even an overwhelmingly unlikely arrangement can cease to be impossible in a probabilistic sense. A scattered deck of cards could, in principle, return to an earlier ordering. A gas could briefly resemble its original concentration. A complicated physical configuration could reappear. The universe could, under particular theoretical assumptions, revisit states resembling its past. But the required timescales are so vast that the statement becomes difficult to translate into human language. For a system with a finite number of accessible microscopic states, recurrence times can grow exponentially with the number of degrees of freedom. For macroscopic systems, the resulting intervals can exceed familiar cosmological timescales by factors so enormous that writing the full number would scarcely make the concept more comprehensible. And there is an important distinction between returning near a previous microscopic state and reproducing an exact human history. A recurrence need not reconstruct your life precisely. It could approach a prior configuration without matching every detail. The difference between arbitrarily close and identical is mathematically significant. Even so, the possibility raises strange questions about memory and identity. Suppose a future configuration becomes nearly indistinguishable from one that existed billions of years earlier. Would it represent a recurrence of the same event, or merely a new event with a similar physical arrangement? If a configuration containing a human brain reappeared, would that person be you? Or would it simply be another arrangement of matter carrying memories that resemble yours? Physics alone may not settle that philosophical distinction. The recurrence theorem also reveals something subtle about prediction. A deterministic universe does not necessarily mean a practically predictable universe. Tiny differences in initial conditions can become magnified through chaotic dynamics. A system may obey exact equations while remaining impossible for any realistic observer to predict over sufficiently long intervals. Poincaré himself made important contributions to the study of chaos and dynamical systems. His work showed that even systems governed by simple deterministic laws can possess astonishingly complicated long-term behavior. The theorem, therefore, sits within a larger lesson about nature. Order and unpredictability are not opposites. A system can follow strict mathematical rules while producing trajectories too complicated to forecast indefinitely. And perhaps the most intriguing question is what happens when such a system is given not thousands of years, but durations approaching the limits of physical meaning. Does history become circular? Does the distinction between past and future weaken? Or does the theorem reveal only a mathematical possibility that the real universe, with its expanding geometry and quantum nature, never realizes? Those questions remain open. The Poincaré recurrence theorem is rigorous mathematics, but applying its intuition to the entire cosmos requires assumptions that have not been established as physical fact. Our universe may be infinite. Its accessible phase space may not be finite. Its expansion may continue indefinitely. Quantum gravity may alter the underlying picture. Or some deeper principle may prevent the type of recurrence imagined by classical dynamical systems. For now, the theorem remains a quiet disturbance in our understanding of time. A system can move forward through an immense landscape of possibilities and, given the right conditions and enough time, approach a configuration it has already known. The clock keeps advancing. The particles keep moving. And somewhere in the mathematics lies the possibility that the universe does not simply leave its past behind, but may, after intervals almost impossible to conceive, circle close to it again. Whether that possibility belongs to the physical cosmos or only to an idealized mathematical world is still uncertain. But if recurrence is woven into the laws of nature, then perhaps the deepest mystery is not whether the past can return. It is whether, on timescales beyond comprehension, anything in the universe ever truly happens only once. The universe appears full of things: stars burning in distant galaxies, planets circling silent suns, clouds of gas drifting between stellar systems. Yet, remove all of it, and a deeper question remains. What is left when space contains no particles, no light, no ordinary matter at all? The answer, according to modern physics, is not simple emptiness. Even a perfect vacuum is expected to possess physical properties. Quantum fields extend through space. Their lowest energy states are not necessarily featureless nothingness. And somewhere inside this apparently empty background lies one of the most unsettling possibilities in theoretical physics. Perhaps the vacuum we inhabit is not the lowest possible state of nature. Perhaps the universe is resting in a temporary configuration, and if another lower energy state exists, the consequences could reach far beyond anything normally associated with cosmic catastrophe. The idea is known as vacuum decay, while the broader problem surrounding the enormous discrepancy between theoretical and observed vacuum energy is often called the vacuum catastrophe. These are related, but they are not identical. The vacuum catastrophe concerns one of the most persistent mismatches in physics. Theoretical estimates of quantum vacuum energy can differ enormously from the tiny effective energy density inferred from cosmological observations. Vacuum decay concerns a different possibility, that the quantum vacuum might exist in a metastable state capable of transitioning to a lower energy configuration. Both problems point toward the same uncomfortable territory. What is the true state of empty space? To understand the question, it helps to abandon the classical image of a vacuum as nothing. Quantum field theory describes particles as excitations of underlying fields. The electron is associated with an electron field. Photons arise as excitations of the electromagnetic field. Other particles correspond to other quantum fields permeating space. Even when no particles are present, the fields remain. Their lowest energy configuration is called the vacuum state. But quantum mechanics prevents fields from behaving like perfectly motionless classical substances. Quantum fluctuations are an intrinsic feature of the theory. The vacuum therefore possesses structure, even when no ordinary particles are present. This idea has measurable consequences. The Casimir effect, predicted by Hendrik Casimir in 1948, demonstrates that quantum electromagnetic fluctuations can produce measurable forces between closely spaced conducting surfaces under suitable conditions. The effect does not prove every popular claim about vacuum energy, but it illustrates something fundamental. Empty space in quantum field theory is not equivalent to absolute nothingness. The difficulty begins when physicists try to calculate the energy associated with the vacuum. Quantum field theories contain contributions from the zero-point energies of their modes. Naively summing these contributions leads to an enormous result. Yet cosmological observations indicate that the effective vacuum energy associated with the accelerated expansion of the universe is extraordinarily small. The discrepancy is vast. It is often described as one of the worst fine-tuning problems in theoretical physics. The precise numerical comparison depends on how the calculation is formulated and what is treated as physically observable. So, the popular claim of a simple, universally agreed 120 orders of magnitude mismatch can be misleading. But the underlying problem is real. Quantum field theory and cosmological observations do not yet provide a satisfying explanation for why the vacuum energy is so small. That unresolved tension is part of what makes empty space so mysterious. The vacuum may be energetically quiet on the scale of cosmology, yet quantum theory suggests that beneath that apparent stillness lies a complicated structure. Then comes the more dramatic possibility. What if the vacuum surrounding us is not the absolute minimum of the universe's potential energy? Certain quantum field theories permit metastable states. A metastable state can persist for an extraordinarily long time while still not representing the absolute lowest energy configuration. A familiar analogy would be a ball resting in a shallow depression on a landscape. The ball is stable against small disturbances. Yet, a deeper valley exists elsewhere. Given enough energy, or through quantum tunneling, the ball could escape its local depression and settle into the lower one. A quantum field can, in principle, behave in an analogous way. The vacuum could occupy a local minimum of its energy landscape, while a lower minimum exists elsewhere. If a transition became possible, a tiny region of the lower energy vacuum could appear. That region would be a bubble of true vacuum. The crucial point is that such a bubble would not necessarily remain tiny. Under the theoretical conditions associated with false vacuum decay, it could expand outward at a speed approaching that of light. Inside the bubble, the fundamental properties of the vacuum could be different. Particle masses could change. Forces could behave differently. The structure of atoms might no longer be stable. The chemistry that permits planets, biology, and observers could cease to exist in anything resembling its present form. There would be no conventional explosion, no warning traveling ahead of the transition, no ordinary signal moving faster than the bubble itself. If such a process were physically possible, an observer could receive no advance notice carried by light from the approaching boundary. The transition would simply arrive. This is the frightening elegance of vacuum decay. But there is an important reason not to treat it as a prediction of imminent destruction. There is no evidence that our vacuum is currently decaying. The scenario is a theoretical consequence of certain assumptions about the fundamental fields of nature. And those assumptions remain incomplete. One field has attracted particular attention: the Higgs field. The Higgs field permeates the universe, and its interaction with elementary particles contributes to their masses. The discovery of the Higgs boson at CERN in 2012 confirmed the existence of the associated field predicted by the Standard Model. Measurements of the Higgs boson's mass, together with estimates of the top quark mass and other parameters, allow physicists to examine the shape of the Higgs potential. Some calculations suggest that the parameters of the Standard Model may place our present vacuum in a region that is metastable rather than absolutely stable. This possibility is often described as a near-critical universe. But the conclusion depends upon theoretical inputs, uncertainties, and assumptions about physics at energy scales far beyond current experiments. Even if the Standard Model vacuum is metastable, the calculated lifetime can be fantastically longer than the current age of the universe. There is no established indication that a transition is about to occur. Still, the idea forces a remarkable question. Why does the universe sit where it does on the landscape of possible field configurations? Was the vacuum selected by fundamental laws? Was it established during the early universe? Could unknown particles or interactions change its stability? Perhaps physics beyond the Standard Model completely alters the calculation. The early universe provides another piece of the puzzle. During its earliest moments, conditions were vastly hotter and denser than anything found today. Fields that now occupy familiar states could have behaved differently under those extreme conditions. As the universe cooled, phase transitions may have occurred. The Higgs field eventually settled into the state associated with the vacuum we observe. Other fields may have undergone analogous transitions. The history of the universe may therefore already contain examples of vacuum-like phase changes. But whether our present vacuum is the final state is another matter. Physicists use the concept of an energy landscape to visualize these possibilities. Picture a vast terrain of valleys and ridges. Each valley could represent a different vacuum configuration, with different physical properties. Our universe occupies one particular valley. Perhaps it is the deepest. Perhaps another lies below it. Perhaps countless valleys exist, separated by barriers that make transitions extraordinarily unlikely. In some theoretical frameworks, the landscape becomes enormously complicated. String theory, for example, has been associated with the possibility of a vast number of possible vacuum configurations. This has contributed to discussions of the so-called string landscape, and in some models, anthropic explanations for why our universe possesses particular physical constants. But these ideas remain subjects of active debate. The existence of a theoretical landscape does not establish that all its possible vacua physically occur, nor does it prove that our universe can transition between them. That distinction is essential. The vacuum catastrophe is sometimes portrayed as though scientists have discovered that empty space contains enough energy to destroy the universe at any moment. That is not what the evidence says. The actual mystery is quieter. Theoretical quantum contributions appear enormous under naive calculations, while the observed cosmological effect is tiny. Some mechanism seems to suppress or cancel most of the expected contribution. We do not yet know why. This problem connects to the cosmological constant, dark energy, quantum field theory, and the deeper question of how gravity responds to vacuum energy. General relativity tells us that energy and pressure influence space-time. Quantum field theory tells us that even the vacuum possesses quantum structure. A complete theory of quantum gravity should ultimately explain how these descriptions fit together. We do not have that theory. Perhaps the resolution lies in a symmetry that cancels vacuum contributions. Perhaps gravity responds to vacuum energy in a way that differs from our simplest assumptions. Perhaps the cosmological constant is a fundamental parameter whose small value must simply be measured rather than derived. Or perhaps an entirely new principle is waiting to be discovered. The vacuum decay problem adds another layer of uncertainty. If the vacuum is metastable, its apparent stability could be deceptive. A system can remain unchanged for timescales vastly exceeding the age of the universe and still possess a lower energy state. That makes stable and eternally stable very different concepts. Yet, the same mathematics that allows metastability can also produce extraordinary lifetimes. A vacuum can be technically unstable while remaining effectively permanent on every timescale relevant to civilization, stars, galaxies, and perhaps even the observable universe. There is another subtle point. The expansion of the universe may influence vacuum transitions. Cosmic inflation, for example, is associated with a rapidly expanding early universe and has motivated models involving quantum fields trapped in metastable states. The details vary enormously between theories. Some scenarios describe inflation as arising from a field slowly rolling down a potential. Others involve false vacuum energy and bubble nucleation. These ideas are not interchangeable, and none provides a confirmed account of the ultimate state of the vacuum. But together, they demonstrate how intimately the fate of the cosmos may be connected to the behavior of fields that are invisible to our senses. The deepest irony is that the universe's most consequential ingredient may be the thing that appears to be nothing. Empty space stretches between galaxies. It surrounds every planet. It fills the laboratory after matter has been removed. Yet, beneath that emptiness are quantum fields whose states determine the properties of particles, forces, and perhaps the expansion history of the cosmos itself. If our vacuum is absolutely stable, then the universe may continue inhabiting this state indefinitely. If it is metastable, an unimaginably rare transition might remain possible. If unknown physics changes the energy landscape, even that distinction could become obsolete. No observation has revealed a bubble of lower energy vacuum approaching through space. No experiment has demonstrated that our vacuum will decay. What remains is a theoretical boundary between what physics can calculate and what nature has actually chosen. Perhaps the vacuum surrounding us is the deepest state reality permits. Perhaps it is merely a quiet resting place, stable enough to endure for times beyond imagination, but not eternal. And perhaps the enormous discrepancy between quantum vacuum energy and the tiny energy density inferred cosmologically is pointing toward a missing principle, one capable of explaining not only why empty space is so quiet, but why it has the particular character that allows stars, matter, chemistry, and observers to exist at all. The universe appears silent when we look into empty space. Yet that silence may conceal one of the greatest unresolved questions in physics: whether the emptiness surrounding everything is truly the final state of reality, or simply the calm surface of a much deeper quantum landscape. A faint point of light crosses the detector, leaving behind a trace that lasts only a fraction of a second. Around it, magnetic fields bend invisible particles into controlled paths, while enormous machines buried beneath the Earth search for the smallest constituents of matter. At this scale, the familiar world begins to dissolve. Protons and neutrons are no longer indivisible objects. They are assemblies of quarks bound together by the strong nuclear force. Yet, there may be another form of matter hidden within those same equations. A substance so dense and unusual that, under certain conditions, it could represent a more stable arrangement of matter than the ordinary material surrounding us. This is the premise behind the strange matter hypothesis. It begins deep inside the atomic nucleus, with particles known as quarks. Ordinary matter is built primarily from up and down quarks. These combine to form protons and neutrons, which in turn form atomic nuclei. The nuclei interact with electrons, and together these structures produce the extraordinary variety of matter encountered throughout the universe. But quantum chromodynamics, the theory describing the strong interaction, permits a much richer possibility. There are 6 known types, or flavors, of quarks: up, down, strange, charm, top, and bottom. Under ordinary conditions, strange quarks are not stable components of familiar matter. They tend to decay into lighter particles through the weak interaction. But under extreme density, the situation may change. Deep inside the cores of neutron stars, matter could be compressed to extraordinary densities. Nuclei may cease behaving as separate objects. Protons and neutrons could effectively dissolve into a dense sea of quarks. And among those quarks, something unusual might happen. Large numbers of up and down quarks could potentially convert into states containing strange quarks. The resulting material is sometimes called strange quark matter. The hypothesis becomes particularly intriguing because strange quark matter might, under certain theoretical models, possess a lower energy per baryon than ordinary nuclear matter. If that were true, ordinary nuclear matter could be metastable, not necessarily doomed to transform spontaneously throughout the universe, but potentially capable of converting into a more stable state under sufficiently extreme conditions. The idea was developed prominently in the 1970s through work by physicists including A.R. Bodmer and Edward Witten, which is why the possibility is sometimes associated with the Bodmer-Witten hypothesis. At its heart lies a deceptively simple question: what is the most stable form of matter permitted by the laws of physics? We know that protons and neutrons are stable enough to form the visible universe around us. But stability does not always mean absolute stability. A physical system can remain in a state for an extraordinarily long period, while another state of lower energy exists. The strange matter hypothesis asks whether something similar could occur at the level of nuclear matter. Imagine compressing matter until the distinctions between individual protons and neutrons begin to disappear. Instead of discrete particles, there could be an almost continuous quantum fluid of quarks. If strange quarks become energetically favorable in that environment, the resulting state might be exceptionally stable. The concept is difficult to visualize because no sample of strange matter has ever been placed inside a laboratory container. Researchers have never held a piece of it, weighed it, or watched it interact with ordinary material. Its existence remains hypothetical. Yet, the physics behind the question is not fictional. Quarks are real. The strong nuclear force is real. Matter at extreme density exists in the universe. Neutron stars are observed astrophysical objects. The uncertainty concerns what happens when these ingredients are pushed beyond the regimes we can reproduce and observe directly. Neutron stars provide the natural laboratory. When a massive star exhausts the fuel supporting its core, gravity can overwhelm the star's internal pressure. The outer layers may be expelled in a supernova, while the core collapses into an incredibly compact object. If the remaining mass is within the appropriate range, the result can be a neutron star. A typical neutron star contains more mass than the Sun compressed into a sphere only roughly 20 kilometers across. The density is staggering. A teaspoon of neutron star material, if somehow brought to Earth and preserved, would possess an extraordinary mass. But the familiar teaspoon analogy should not be taken literally, because such matter cannot simply exist under ordinary terrestrial conditions. Inside the star, pressure and density increase dramatically toward the center. The outer layers may contain atomic nuclei arranged in exotic phases. Deeper regions could contain densely packed neutrons. Further inward, the familiar description becomes increasingly uncertain. Could quarks become deconfined? Could strange quarks appear in large numbers? Could the entire star become a form of quark matter? These are active theoretical questions. Some models predict ordinary neutron stars. Others permit quark stars. Still others allow hybrid stars, in which a hadronic outer region surrounds a quark matter core. The difficulty is observational. A distant neutron star does not arrive with a label explaining its internal composition. Astronomers can measure its mass, radius, rotation, magnetic field, temperature, and gravitational effects. But determining precisely what lies tens of kilometers beneath its surface requires theoretical inference. Recent gravitational wave observations have given researchers new information about the behavior of dense matter during neutron-star mergers. When two neutron stars spiral together, they distort spacetime and emit gravitational waves. The final collision can also produce electromagnetic radiation and heavy elements. The detailed waveform carries information about how easily the stars deform under tidal forces. That deformation depends on the equation of state of dense matter. Such observations therefore provide indirect clues about the material inside neutron stars. So far, no observation has established the existence of strange quark matter. But the possibility remains scientifically interesting. There is another reason. If strange quark matter is absolutely stable, a tiny fragment could theoretically exist as a compact object known as a strangelet. A strangelet would consist of a finite quantity of strange quark matter rather than an entire star. Theoretical properties depend heavily on the model, but strangelets are often imagined as extremely dense objects containing roughly balanced populations of different quark flavors. This leads to one of the more dramatic scenarios associated with the hypothesis. Suppose a stable strangelet encountered ordinary nuclear matter. Could it convert that matter into strange matter? In some speculative models, the answer could be yes. The strangelet would act almost like a seed, allowing nearby nuclear matter to reorganize into the lower energy state. If such a process were possible, a sufficiently stable strangelet could theoretically grow by consuming ordinary nuclear matter. The idea has occasionally produced fears surrounding high-energy particle accelerators. could collisions at facilities such as CERN create a strangelet capable of transforming the Earth? The scientific consensus has not found evidence for such a danger, and detailed safety analyses have argued that the scenario is extraordinarily implausible. Nature itself provides an important counterargument. Cosmic rays have been striking Earth, the Moon, and other astronomical bodies at energies comparable to or greater than those reached in human-made accelerators for billions of years. If ordinary collisions at those energies routinely created dangerous stable strangelets, we would expect to see their consequences across the universe. We do not. That does not prove strange matter cannot exist. It strongly constrains the circumstances under which it could be dangerous. The distinction matters. A scientific hypothesis can be fascinating without being a prediction of catastrophe. The strange matter question is primarily about the behavior of matter under extreme conditions, and those conditions may exist naturally inside some of the densest objects in the cosmos. There is also a deeper connection to the structure of the strong force. Quarks are never normally observed in isolation. This phenomenon, known as confinement, is one of the defining features of quantum chromodynamics. At sufficiently high energies or densities, however, quarks may behave collectively in ways that differ dramatically from ordinary nuclear matter. Physicists have created quark-gluon plasma in heavy ion collisions, briefly producing matter at temperatures comparable to those believed to have existed moments after the Big Bang. But quark-gluon plasma is not the same thing as cold, dense, strange quark matter. The two occupy very different regions of the possible phase diagram of quantum chromodynamics. One is dominated by extreme temperature. The other would involve extraordinary density. That distinction becomes important when considering the early universe. Immediately after the Big Bang, the universe was an intensely hot, dense environment filled with fundamental particles. As expansion continued, it cooled. Quarks became confined into hadrons, including protons and neutrons. Could conditions during that primordial era have produced strange matter? The answer remains uncertain. Some theoretical models have explored the possibility that stable quark matter could have survived from the early universe in the form of compact relics. Others find no compelling reason for such objects to persist. No confirmed observation has demonstrated that primordial strangelets exist. Still, the possibility illustrates how a question about subatomic particles can reach across cosmic history. There is another extraordinary implication. If strange quark matter is more stable than ordinary nuclear matter, perhaps some neutron stars are not merely dense collections of familiar particles. Perhaps they represent a different phase of matter altogether. Such an object might have different cooling behavior, rotational properties, mass-radius relationships, or responses to tidal forces. Researchers can search for those signatures. A definitive discovery would be profound. It would reveal a new state of matter and provide a direct window into quantum chromodynamics under conditions impossible to reproduce for long periods on Earth. But nature has not yet offered an unambiguous answer. Some candidate observations have generated discussion. Unusual compact stars. Unexpected mass-radius combinations. Objects that may be difficult to reconcile with particular neutron star equations of state. Yet, none has established strange stars as a confirmed class. Alternative explanations remain available. Dense nuclear matter is notoriously difficult to model because the relevant interactions become extraordinarily complicated. Different assumptions about nuclear forces, quark confinement, particle species, superconducting phases, and high-density equations of state can produce substantially different predictions. And there is an even deeper possibility. The familiar categories of particle and matter may become inadequate at such densities. Quantum chromodynamics allows phases in which quarks pair together, producing forms of color superconductivity. One proposed state is known as color-flavor-locked matter, in which quarks form a highly organized quantum phase involving color and flavor degrees of freedom. These ideas remain theoretical, but they demonstrate how radically matter could behave when pushed beyond ordinary nuclear conditions. The periodic table describes the chemical world with extraordinary success, yet it occupies only a narrow region of the possibilities permitted by fundamental physics. Beyond it lie states of matter that exist only briefly in laboratories, or perhaps only inside stars. The strange matter hypothesis sits somewhere along that boundary. It is grounded in established theories while extending those theories into regimes where direct evidence is scarce. Perhaps strange quark matter exists only inside the deepest regions of neutron stars. Perhaps it forms stable stars unlike anything previously identified. Perhaps tiny strangelets drift through space as relics of violent cosmic events. Or perhaps the entire idea fails because ordinary nuclear matter is ultimately more stable than the calculations suggest. The uncertainty is not a weakness of the question. It is the reason the question remains alive. Somewhere across the galaxy, a neutron star may be carrying a secret beneath its surface. Its gravitational field reveals its mass. Its radiation reveals its temperature. Its rotation tells us about its structure. Gravitational waves may reveal how it deforms. But none of these observations yet provides a complete view of its deepest interior. And there, under pressures that crush atoms into unfamiliar quantum states, matter may be taking a form that Earth has never naturally produced. The universe could contain an entire phase of substance hidden inside its densest stars, waiting for the right observation to reveal it. Or the equations may be leading us toward a possibility that nature never chose. For now, the question remains suspended between theory and evidence. When matter is compressed beyond the architecture of ordinary nuclei, does it become something fundamentally new? And if so, how far does that transformation extend?